Okay, let's take a look at a more complicated reaction. This one has two reactants, and so we can have independent orders of each of the reagents, and then there's an overall order as well. And this time we're going to look at a data table and determine the dependence of, or the order of each of the reagents. First of all, if we have two reagents, our rate is always going to be the rate equal to rate constant times reagent A to some power n or x, whatever, times the concentration of the other reactant to a different power, right? Where the superscripts n and m are representative of the order of each of the reactants, and if you add the two, that gives you the overall order. So if n and m are equal to 1, it's first order with respect to NO2, and it's first order with respect to CO, and the overall order rate is second order. And so how do we, based on the experimental data, determine the rate of each of the reactants? And in order to do that, we try to keep one of the concentrations constant and see how doubling or tripling the concentration of the other reagent affects the rate. So here we are given 4 data points, and we are supposed to determine the order, basically, right? So what you want to do is, if you look at data point 1 and 2, and you can tell that the concentration of carbon monoxide here is kept constant. So the rate effect here, which is quadrupling here, right? We go from 21 to 82. That's 21 times 4. So that means the rate of this reaction has quadrupled. And that's because we doubled the concentration of NO2. And so the only reason we can now argue that N is going to be equal to 2 is because we kept the carbon monoxide constant, right? So we know that the doubling has nothing to do with the concentration of CO, which we kept constant. So this is the kind of thing you want to look at on a data table. 2 points where you kept the concentration constant. And you can also look at these 2 points here, right? So here you also are keeping the concentration the same. So going from 20 to 40, that should also quadruple, and that's as well true. So you can take any of these points and get the reaction order. So we already know N is second order here. And so now how do we get M? Well, we do the same thing. We pick now 2 points of this data where we're keeping the concentration of nitrogen dioxide constant. And so that's from 2 to 3. So from 2 to 3, we are keeping the concentration of NO2 the same, and we're doubling the concentration of CO. And here, the reaction rate doesn't change at all. So we know that M here is going to be equal to 0. So it's independent of the concentration of CO. So the rate is going to be equal to some sort of K times the concentration of NO2 to the second power. That is the rate law of the reaction. And so now if I wanted to determine the rate constant K, I can take any of these data points, the first, second, third, or fourth, and just plug the data in. Right? Don't have to worry about this. It's not part of the rate. But let's just make it simple and plug in this first one. So K is going to be equal to the rate, in this case 0.0021 m per second, and we will divide that by the concentration of NO2, which is 0.10 m squared, and that equals 0.21 per m per second, which is what we expect the constant for a second order rate to be. Now you can also do this mathematically. We'll look at that in a second, but here's a summary of the rate and the calculation that I just showed you. And so the book suggests that it gives you a graphical illustration of what I just went through. And so here it's showing you that the concentration is constant, you're doubling the concentration, and you're quadrupling, which means we have second order. I don't really think that you need to look at this illustration. I think it's pretty straightforward. Let's looking at the chart, which points to put out, pick up, and right. Okay. Well, let's just move on to the next problem. This is a similar problem. Same question. Write a rate expression and calculate the value of the rate constant. So we know we have two reactants here, and the rate will be equal to some sort of K times the concentration of NO2 to some power N times the concentration of F2 to some concentration M. And so again, we go from the first to the second. We are doubling here the concentration. The rate doubles, and really important is that we're not changing the concentration of the second reactant. So we know that this is first order. So the rate equals K times the concentration of NO2. So N is going to be equal to 1. And so let's determine the order rate of fluorine here. And so now we're going to look at data point 2 to 3. So from 2 to 3, we're keeping NO2 constant now. We're doubling here times 2 the concentration of fluorine. And again, you're doubling the rate. So it's also first order. So the second reagent, F2, also to the first power. And of course, you don't need to write those exponents there. It's just K times the concentration of NO2 times the concentration of F2. And so it's overall second order because you're just adding up those exponents. So overall it's second order. And then it's of course always asking for the rate constant here. What is the overall order of the reaction? It's not asking for it, I guess, but you can solve for K if you wanted to. Again, all you have to do is plug in one set of data. K is going to be equal to the rate. Let's pick this first one here, which is 0.026 mol per second, divided by the concentration of F2, which is 0.100 times the concentration of NO2, which is 0.100. I should put the units in M and M, so this cancels, and your units are going to be per mol and per second. You can solve this mathematically. In fact, we're going to do this in the lab for reactions asking you to set up these. But mathematically, it looks at rate 2 versus rate 1. And you can do this for any of the points, whether you're keeping one constant or not. But it's just the math is just easier if you're keeping 2 the constant. But you could do that. Rate 2 versus rate 1 is going to be equal to the rate expression to some power n and m times the concentration here, right? And so but if we're plugging in 0.1 and 0.1, see that just drops out of the equation, and when you solve for n, for example, or for m here, the math becomes pretty easy, right? So if you, and I'm not going to show you how that works, but here's is our rate law. Next, we're going to look at integrated rate law. What that does is it takes our data. First of all of these reaction orders, first, second, and zero order, they behave differently, and so we're looking at different data. And if we can take this data and manipulate it to where we can have a linear relationship, such as shown here. So if you, for example, for a first order reaction, if you take your data and you plot time versus the natural log of concentration of T, it becomes linear. And what that does is we can come up with an equation that allows us to determine K based on our data simply by solving for the equation, and the slope is going to be equal to negative k in this case. So that's nice, right? It also allows us to use this equation to determine the concentration of our reagent or reactant here at time t, just by plugging it in instead of measuring, so we can predict that. So that's quite handy, right? And the reason I have this over here on the left is for a couple of reasons here. So this is an example of what real life data would look like. Here we have a lot is plotted here. So in green we have one of the reagents and the concentration with respect to time, and so we can see that the rate, as it decreases, it changes slowly, becomes smaller and smaller as time proceeds, and so that rate is constantly changing. We can of course calculate the rate at any point by drawing a tangent and then calculating the slope rise over run, and that is going to be equal to the rate at a particular point. And so this would actually be representative of first order and second order. You would have to actually apply some math to see if it's first or second order. You have to do better than that. And of course here in red, just as a side note, is going to be an increase, because it's the increase of the product or the concentration of the product as the reactant proceeds, or the reaction proceeds. And so obviously that goes up as green goes down. All right, so let's take a look at a summary of the first order reaction. So again, really important. You have access to that on that very slide in the beginning of lecture 2 that I pointed to you that you need to have in front of you. Here I have it in front of me, so I hope you have yours. So you'll be given the integrated rate law. You should be able to use it to calculate the concentration of the reactant at any time, given the time, given K. We'll work a few problems. And we're also going to look at something called the half-life. You'll be provided with that. For first order reaction, turns out that that's a constant, which means that the time it takes to cut your sample in half is independent of the concentration. And so that makes it actually very convenient to calculate, whereas for second order, it's not equal to a constant. That actually changes. What that also means is that for a reaction like that with first order, it'll never really go to completion, because your rate's always going to be able to cut in half when it slows down. It basically levels out and never hits the x-axis. So let's work this example and then take a break. So the decomposition of SO2 Cl2 is first order and has a rate, so that's great, right? It's telling you it's first order, and then so you go look at your chart, you can find your integrated rate law, or if it's asking for half-life, you can look up the half-life. But so that's good and important, and it gives you a rate constant, so they give you K, and then they tell you that the reaction is carried out at the same temperature. That's important because your rate can change. Temperature affects rate, so it needs to be done at a constant temperature. We can't use the integrated rate law. That's always a given. If that's not said, you can assume it, or we don't really have a problem to solve. And then the concentration, the initial concentration is given, and it's telling you the time. And so they want to know what happens, what is the concentration of this reagent at 865 seconds. And so you go dig out that integrated rate law for the first order, and so that's going to be equal to the natural log of concentration A at time t equals to negative kt plus the concentration of A at time 0, which is the initial concentration. So you just plug those values in, and then you solve for that. So the natural log, and so the concentration at time t, that's what we're after. So I'm going to replace t with 865 seconds. That's just so I know what I'm solving for. Times negative k, I'm provided with k. That's 2.90 times 10 to the minus 4 per second times t, which is 865 seconds. That's provided, and so we right away have unit canceling here, plus the concentration of the initial concentration of A or S O2Cl2, which is given to us. Sorry, I forgot, of course, the natural log. Wonderful, right? So this is also the natural log of A. Let me rewrite that. Plus the natural log of A at time 0. So plus the natural log of 0.0225 m. If I take the natural log of that, I get negative 0. Sorry, it's 3.79. If I take 2.9 times 10 to the minus 4 multiplied by 865, I get minus 0.251. I add the two together, I get that the natural log of A at time 865 equals minus 4.04. So the last step is solving for the concentration of A at time 865 seconds. So I take the inverse natural log, which is Euler's constant, to that number over here, to the minus 4.04, and you need to just figure out how to use this in your calculator, and when you solve that, you get a concentration of 0.0175 m. Alright, so when we come back, we're going to look at second order rate loss, and we're going to look at how to graph on Excel again. I'm tired, so I'm going to take a break. Of course, by the time you listen to this, the other lecture's up already, so might as well go ahead and watch another one. I'm going to go take a nap.